So, we will do some special topics, and these topics come as applications of Fermi statistics that we have learned. So, we learn how to actually map Fermi surface of metals, real metals that is. We of course know that how the Fermi surface of a free electron gas or collection of fermions, non-interacting fermions, they look like. Or rather a degenerate gas of fermions look like, but we will just revise that once more. And in that connection we will do the Haas-van Alphen effect, which was done in 1930 on bismuth by de Haas and van Alphen, and this relates oscillations of the magnetic susceptibility as a function of the external magnetic field. And of course, we are talking about 3-dimensional materials here. 2-dimension is special, and the application of magnetic field in 2-dimension gives rise to a number of interesting consequences, and quantum Hall effect is one of them. And I suggest that there is another MOOCs course of mine on quantum Hall effect, which you can have a look at, which in details talks about the effect of this transverse magnetic field or perpendicular magnetic field on electrons that are confined in 2 dimensions. These are free electrons, and this gives rise to the what is called as the integer quantum Hall effect. I will not talk about it here, rather we will talk about these applications of magnetic field in real materials and these mapping of the Fermi surface. So, just to remind you, the Fermi distribution function if you plot it as a function of f of epsilon, and if you plot this as beta epsilon minus mu, where epsilon are the single particle energies, mu is the chemical potential, and beta is 1 over T or 1 over kT, and we get a distribution which looks like this, and all these states inside the this box that you see, or the step function that you see, are filled, and all the states that are larger than epsilon equal to mu is empty. So, this actually corresponds to epsilon equal to mu, and so this mu at t equal to 0 is called as the Fermi energy, okay, and we denote it by epsilon f, and one can write it, or rather relate it to this h cross square kf square over 2m, where kf is called as the Fermi wave vector. And what is a Fermi wave vector? So, if you have n electrons, and if you start putting them in this say this kx and ky and kz direction uniformly, so you fill in states and pertaining to the condition of the Pauli exclusion principle, and then you keep filling these n particles or n fermions, and if you grow isotropically from the origin by putting them, and if you have n electrons, you actually get a Fermi surface which is spherical in shape, and that Fermi surface has radius which is given by kf, and that is called as a Fermi wave vector. Now, when you go to finite temperature, so let us just talk about plotting it versus epsilon minus mu, and then when you do it at finite temperature, this really gets modified just a little bit, and so some spectral weight from here, let me draw it by a color. So, this region that appears here, and the concept of Fermi energy is no longer valid, and because the Fermi surface, the sharp Fermi surface goes away, but one can still define what is called as a chemical potential. And this chemical potential, as you know, that even at temperature which is room temperature, this distribution is minimally affected. The reason being that the corrections to the Fermi distribution function is what we have seen. It goes as kT over epsilon f square. I mean, the leading order correction goes as this, and this kT at room temperature is about 0.0025 electron volt, while epsilon f, so this kT, this at room temperature, which is 300 Kelvin, and epsilon f typically is about say 5 or 6 electron volt, and this tells you that this is several times larger, like 10 to the power 4, 5 times larger than the, so the Fermi energy is this much 10 to the power 4, 5 or 6 times larger than that of kT, and one actually talks about these correction to be very small. And so, the leading order correction to various quantities such as susceptibility or specific heat, that goes like this, which come from the Sommerfeld expansion, and all the activities, that is all these when you give certain temperature, these are the electrons that are going to be promoted to energy which is larger than the Fermi energy, and this width is really the kT, and each of these electrons have energy at temperature T as kT. So, the total energy goes as kT into kT, because this is a fraction of electrons that are excited. So, it is kT into kT, so that gives you a kT square, and hence the specific heat due to electrons go as T. This is what all we have learned. And the Fermi surface, of course, is a spherical Fermi surface with a radius kf, but it is important for us to understand that how the Fermi surface is determined for a real material, and this is called as a de Haas-van Alphen effect, and it requires one to include a magnetic field, and let us see how things can be done there. So, and why is Fermi surface or Fermi energy so important? Because the states that are closest to the Fermi surface, they are the ones that contribute to the transport properties and various other properties. Just like what I said, the distribution, it's only the electrons that are edge of that step function, they only take part in various physical processes, and that is why they are important. So, we need to really know or map out the Fermi surface and get some information about it, how it looks like, what is the curvature and so on. Of course, for a free electron it is just a sphere, but for real materials it's not, and it has to be determined. Okay. So, the various physical properties depend upon the Fermi surface. This is what the main message is. And we will call it Fs in short if it comes, and so the shape is determined by, shape of Fs is determined by, we use another abbreviation called as DHVA effect, which is called as a de Haas-van Alphen effect. Okay. So, which is actually the oscillation of magnetic susceptibility and as a function of the field. Once again, I will not do a very sort of elaborate account of this. In fact, magnetic susceptibility is still an equilibrium quantity, but if one wants to do the Shubnikov-de Haas oscillations of the either the resistivity or the conductivity, that is a nonlinear or rather that requires one to go to non-equilibrium stat mech, and one needs to take into account the kinetic theory. And we only concentrate on the de Haas-van Alphen effect, and so this was done by, as I said, de Haas and Van Alphen, and in 1930, and they did it at pretty low temperature. This was at about 14.2 Kelvin, found out the Fermi surface of bismuth. Okay. And so, just to tell you a priori that m over b, that shows oscillations, or h over the magnetization, or this is called as a susceptibility. So, chi is equal to m over b shows oscillations as a function of 1 over b, where b is the magnetic field. Okay. So, there are certain prerequisites that need to be satisfied, and these prerequisites are the orbits of electrons. So, one of them is the orbits of electrons remain well defined. This is a very important thing, that even if the electrons scatter in real materials, still the orbits are well defined. It can be actually stated in this fashion that in fact, these electrons execute various orbiting motions before they get scattered. Okay. So, this tells you that the scattering is minimal. I mean, scattering effects are minimal, and they are there, but they do not destroy the orbits. And also it is true that the quantization of the orbit remains robust. So, these are quantization of the electronic orbits, and of course, we need two more things: a large magnetic field and small temperature. And small temperature because the thermal effect should not smear the Fermi surface completely. So, we should be at very low temperature. Okay. We will just come to this in a moment, and let me sort of do a simple minded analysis and keep the analysis as simple as we can. So, we write down the equation of motion for electrons in a magnetic field. So, EOM stands for equation of motion, and which is nothing but F equal to H cross k vector dot. So, that is a H cross k dk dt, and that is in presence of a magnetic field. It is E into V cross B, E being the electronic charge, V is the velocity of the fermions or the electrons, and B is the external magnetic field. Now, consider the component of the magnetic field that is perpendicular to V. So, this V t is a component of V perpendicular to B. Okay. So, which means that you do not need to worry about the sin theta between them. So, sin theta equal to 1, and in that case you can write down a dk is equal to E b over H cross and a V t dt. Just simply write dk dt as so as this equation. So, dk is equal to this, and so the time taken for the electrons so to complete one cycle is given as t equal to 2 pi over omega b, and this is H cross by E b, and this is a dt by V, and so omega b of course is equal to E b over m, and so there should be a m here, and so this is a dt over V, and this omega b is called as a cyclotron frequency. So, just to remind you that in presence of a magnetic field, the electrons actually perform orbits, and these radii of the orbits are inversely proportional to magnetic field, which means that if magnetic field is large, and here we actually talk about large magnetic fields, and then the radii become smaller and smaller. In fact, this is one of the pictorial ways to visualize how quantum Hall effects occur, and it's basically a edge phenomena, and the electrons that are inside the so this is a 2D electron gas, and you have all these electrons performing these cyclotron orbits here. They don't contribute to any kind of transport, but these ones, they cannot complete a full cycle and they kind of skip. So, these are called as skipping orbits, and these do not get scattered at all. So, they remain very robust, and they continue to conduct all these the current, and one gets a Hall current and eventually the Hall conductivity because of this motion of the electrons at the edges. So, these are the cyclotron orbits, and these they are given by EB over m. And now, we sort of know that your Vt and P are perpendicular to each other. And so, we know that a constant magnetic field cannot change the orbit of the electron, or rather the energy of the electron. Hence they should move, they means the electron should move in constant energy surfaces and these constant energy surfaces where their velocity is given by the band velocity. So, velocity is 1 over h cross. So, this is del E del k, and the motion is perpendicular to the constant energy surface. Okay. So, the motion of the electrons is perpendicular to the these constant energy surfaces, and this constant energy surfaces are important for us to determine, and they denote these Fermi surfaces. And this Fermi surface, a typical Fermi surface for say bismuth looks like this. See a complicated structure, and this is what has been found out. So, the Fermi surface is mapped by putting the material or this bismuth in magnetic field, perpendicular magnetic field, and you look at the direction of the particle, or rather the motion of the particle in a direction that is perpendicular to the magnetic field. So, all these surfaces that you see, these are the constant energy surfaces where the electronic motion is perpendicular to these surfaces. Okay. All right. So, this DHVA effect, which is the de Haas-van Alphen, that relates the energy of an electron to the area of the orbit in k space. Okay. So, basically in real space they also move in circular orbit, and in k space also they move in circular orbit, and consider two close by orbits. In k space. So, we consider this orbits in the k space, and these orbits, they look like they are circular orbits, and so we consider two consecutive orbits and consider a point here. So, the velocity of the electron is perpendicular to this, or it is in the radial direction basically, and this is the tangential velocity. So, this is the tangential velocity, and so this is that angle theta that it makes, and in k space the area, or rather the radii are they differ by delta k, and this is one constant energy surface and this is the next constant energy surface, and so on. Okay. So, the velocity is these are basically the orbits, velocity is perpendicular to the orbit. Okay. So, here V t is equal to V sin theta, and so your B is in this direction. Okay. So, it is V sin theta which is equal to 1 by h cross, and you del E del k will write it as delta E delta k, and then you have a sin theta. So, if you actually bring this sin theta delta k over sin theta, then that becomes equal to 1 by h cross delta E by delta k, the transverse component of that, which is delta k over sin theta. So, the time period of motion is given by t equal to 2 pi over omega b, which is equal to h cross over E b, and now we have a dk divided by delta E divided by delta k transverse. Okay. So, that is the time period, and if you do it carefully, then it becomes h cross by E b delta E and delta k t dk, and this is equal to h cross by E b delta A by delta E. So, just to tell you that delta A is basically the area between the two constant energy surfaces. So, this is the energy difference, rather the delta A I am talking about. Delta A is the area of the concentric region. So, we have considered magnetic field and have considered electrons, free electrons that are subjected to this. So, they would execute these. So, the equation of motion is given by this, which is minus E v cross b, that is a force, and then we take a component of the velocity that is perpendicular to b, and then write down this dk, and then we can actually calculate this 4 pi k squared dk, and so these will give you the area of these orbits, and then we calculate what is the time taken for the electrons to complete one orbit, a full orbit, with this velocity that is perpendicular to b, and then we consider two such orbits with this velocity perpendicular to the b, and find out that the time period of motion of the electrons around this orbit, it goes as h cross by E b delta A by delta E. Okay. So, what does it give you? The energy is of course energy of the electrons that we know is given by n and k z. This is n plus half h cross omega b plus h cross square k z square over 2 m. Now, there is something important here. We in 2D with a parabolic dispersion, we have this density of states that is constant, and this is like epsilon f. So, this is the density of states, let us call it d epsilon or g epsilon, whatever you want to call it. And now, this is the without any magnetic field. Now, with magnetic field you have these Landau levels that are formed at equal intervals, and these are n equal to 0 Landau level, n equal to 1 Landau level, n equal to 2 and so on, and these the energy difference between them is h cross omega b, that is the cyclotron frequency, and that is the d of epsilon that it looks like. Okay. So, density of states which is constant and up to EF now gets into sort of they split up into various these discrete levels. So, the density of states looks like a delta function, a series of delta functions formed, these are called as the Landau levels, these n equal to 0, n equal to 1, n equal to 2 are called as the Landau levels, and the energy spectrum looks exactly like harmonic oscillator in presence of a magnetic field. This is a two-dimensional electrons, and this in the third dimension it still behaves like a free particle. Okay. So, there is a magnetic field that is perpendicular. So, in the direction of the field it still goes as a free particle, and in the plane the magnetic field makes these energy levels of the electrons quantized, and these are called as the Landau levels. And these Landau levels, the important thing about the Landau levels is that they are heavily degenerate. They are and the degeneracy is it goes like b over some phi 0, where so this degeneracy per unit area. So, this is called g over a, that is b by phi 0, where phi 0 is called as a flux quantum, which is h over e. Okay. So, we are taking that input, that the energy level in 2D is n plus half h cross omega b, n being the Landau level index, and these are from n equal to 0 to n equal to 1 to n equal to 2 and so on. So, the energy difference between orbits between various circular orbits that we just talked about is h cross omega b, and so one should be able to relate now the delta A, that is the energy of this concentric region, delta A to these h cross omega b. Okay. And this is a task at hand, and that is not difficult, because your delta E is equal to E b by h cross square 2 pi over omega b and into h cross omega b, and this becomes equal to 2 pi. So, this 2 pi E b by h cross. So, delta A, that is the area between the two concentric surfaces, they depend only on B. Okay. So, now consider a three-dimensional problem. So, extend to 3D, because real materials are 3D. And what happens is the following. So, you have all these orbits, and they extend all the way up to the third dimension, and so this the B is shown as perpendicular to that, and you have these tubes. These can be called as a Landau tubes, and these Landau tubes are kind of stacked like this, whose projection is shown here on the plane. And basically we will see that these red dotted line that you see is actually the Fermi surface. Okay. So, this is the scenario. So, you have these electrons orbits, now they are stretched into 3 dimensions. So, they become like all these pillboxes. So, these each of these of course uncovered pillboxes, and they kind of get stacked. And we will see that this has nice implications on the kind of things that we are trying to talk about. So, we extend it to 3 dimension. So, it will create quantization along the z axis because of this h cross square k z square by 2m, and we have these Landau tubes that are formed. And what happens is that as we increase the magnetic field, the cross sectional area increases. So, all these magnetic fields that you see, all these rather tubes that you see here, as you increase the magnetic field, so the tube has larger and larger surface area. So, we just write that. So, as B increases area of the tube, we call it as a Landau tube. So, let us call it as LT increases. Okay. Now, it is very important to realize that for some particular value of the field, the cross section becomes so large that it breaks away from the Fermi surface. Okay. So, now why this breaking away from the Fermi surface happens is the following, that the corresponding energy, as you keep increasing B, the corresponding energy becomes larger than the Fermi energy. So, basically the states inside the Fermi surface, they get pulled out, and that is why in this situation what will happen is that the energy, so this electron actually jumps into the next cylinder. Okay. So, this is what happens. So, this tube, so it goes from one tube to another as the magnetic field increases. So, it kind of jumps from one tube to another, and this actually causes the oscillation. Oscillation is whatever physical quantity that you are looking for, because it jumps from one Landau tube to another. Okay. So, the electrons jump from one LT to another. Okay. So, this causes oscillations in the magnetic susceptibility. Okay. So, now the energy difference between the two tubes say with indices n and 0 is say a n minus a 0, that is the n, the area difference, let us call it as delta A. This is proportional to B and the Landau level index, or this Landau tube index that we have talked about, and n is of course equal to 0, 1, 2, 3 and so on and so forth. Okay. So, A denotes the cross section Fermi surface perpendicular to B, the magnetic field basically. Okay. So, we get these oscillations, and let me just come back to the oscillations in a moment. And so, let us say that B1 and B2 are two values of the magnetic field. Corresponding to two tubes. Okay. So, we have 1 over B 2 equal to 2 pi E by H cross A 0 n plus 1, and 1 by B 1 equal to 2 pi E by H cross A 0 n. So, 1 over B 2 minus 1 over B 1, that is let us call it as delta of 1 over B, that is equal to 2 pi E divided by H cross A 0. So, the reciprocal of the field difference is given by 1 over f, that is equal to delta of 1 over b, which is nothing but 2 pi E by H cross A 0. Okay. So, this frequency is basically noted in experiments, which is what you see here. So, this chi is plotted as H, or is actually B. It can be 1 over B as well, then it looks a little different. In any case, here it is shown, the original experiment is shown, and you see that there are these oscillations of chi, which is the magnetic susceptibility. So, I did not go into details, but what is important here to realize is that one can relate the free energy of these electrons by using Onsager's relation to this area that we have just found, to this area of this orbit or the tubes, the cross sectional area of the tubes. And so, one calculates free energy, and from there one can calculate the magnetization and magnetization. So, calculate free energy relating to area and so this is F, and then use m is equal to minus 1 over V del F del B, and this is the magnetization, and from there the susceptibility is obtained as m over B. Okay. So, this is what is plotted in experiments, and one actually gets these frequencies, and this frequency as it is shown here, it truly is proportional to the inverse of the area of the tubes, and this by mapping these frequencies, or by noting these frequencies, one knows the area of these the surfaces, or the cross sectional area, or the area of the orbits, which helps one to map the Fermi surface, because this is where suppose there is a Fermi surface like this. Okay. So, one actually measures these orbiting areas, and they are related to the B, basically the perpendicular to that, and then knowing these motion of electrons in each point helps one to map the Fermi surface. I of course did not do a very elaborate account of that, but just to give you an idea that there are these experiments which are very important, the initial experiments on bismuth done nearly 100 years back now, 1930, and this was shortly after Landau had shown that the electrons they behave like the oscillators, quantum harmonic oscillators, in presence of a magnetic field, and the formation of Landau levels etc. were shown at that time, and immediately afterwards all these experiments, that is utility of magnetic field in decoding the properties of fermions in a given material is found out. And of course, I have just shown a sort of representative Fermi surface. It is certainly not spherical, and it won't be, because there is no parabolic dispersion, that is E equal to k square kind of dispersion is never there in real material, and on top of that there are thermal effects, there are scattering effects, and there are electronic interactions which all go ahead and renormalize these k square kind of dispersion. So, it is hard to predict unless one knows, through experiments one knows the Fermi surface, and as I said that these electrons at the Fermi surface takes part into all kinds of important phenomena. such as superconductivity, such as even magnetic behavior, etc., or specific heat and so on. And so that is why it is important to know the this Fermi surface and how it looks like for a given system. Okay. So, I will stop here today, and thank you very much.